Okay, but now remember, n is a very large number, right? It's a 1,000-digit number. We are still looking for a needle in a haystack because we are looking for this non-trivial square root of 1 mod n. There are only 2 of them. 2 out of these 10 to the 1,000 numbers. What chance have we of finding them? So this is where we use another kind of approach. So let's again do this by example, and then we'll see the general principle. So let's pick a number mod 21. So let's say we pick a number like 2. And now we look at the powers of 2. Okay, so let's look at 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. But we are looking at everything mod 21, right? It's always mod the number we are trying to factor. How about 2 cubed is 8 mod 21. 2 to the 4 is 16 mod 21. 2 to the 5. Well, it's 32, but what's 32? It's 32 is 11 mod 21. 2 to the 6 is 11 times 2 is 22. What's 22? It's 1 mod 21. Okay, so now is it significant that 2 to the 6 is 1 mod 21? Well, yes, it is, because what this tells us, since 2 to the 6 is congruent to 1 mod 21, what this tells us is that if we take 2 cubed and we square it, this is 2 to the 6, which is 1 mod 21. So this means that 2 cubed, this is a non-trivial square root of 1 mod 21. Right? But what's 2 cubed? That's 8. Remember, that was the number that we found, which was a non-trivial square root of 1 mod 21. So we have found 8 squared is congruent to 1 mod 21. Okay, so now what's the general principle underlying all this? So here's a general lemma, which I won't prove, but if you wish to understand how to prove it, you can look up the reference that I gave. So what it says is that this happens in complete generality. So let n be an odd composite. Now, and let's say that n has at least 2 distinct prime factors. You know, that's the case that we are interested in, because now we want to factorize n. And it says, suppose we pick x uniformly random between 0 and n minus 1, and which is relatively prime to n. Because if it's not relative, so we'll pick an x uniformly random between 0 and n minus 1. If GCD of x and n is not equal to 1, then we're already done, because we've managed to factorize n. So, but if GCD of x and n is 1, which is the usual case, then with probability at least a half, the order of x mod n is even, and x to the r over 2 is a non-trivial square root of 1 mod n. What do we mean by this? So what we mean by this is pick an x at random mod n. So this was like picking 2 mod 21. And now you find the minimum non-zero, minimum positive power of x mod n. So find what power you must raise it to so that you get 1. Okay. So this r is called the order of x mod n. So now what this lemma is telling us is, if we pick x at random, then half the time we'll be in the good case where r is even and x to the r over 2 is not congruent to plus or minus 1 mod n. So if we call this x to the r over 2y, Then we have the case that y is not congruent to plus or minus 1 mod n, but y squared, which is x to the r, is congruent to 1 mod n. So we found our non-trivial square root of 1 mod n, and we can use it to factor, as we saw before. Okay, but this still leaves us with a problem. How do we actually compute this? You know, we found, you know, we pick an x at random. It's going to work with probability half. That's great. But how do we find this order of x? Because the order of x can be very, very large. It can be, you know, comparable in size to n. But n, remember, is a 1,000-digit number. So n is like 10 to the 1,000. So the order might be this huge number, and we can't be raising x to every power. So what's the shortcut? Okay, so let's go back and let's look at what we do. So let's make up a you know, so we've picked this number x equal to 2. We are working. We have n equal to 21, and now let's just build up a table. So let's build a table where here we have the number a, and here we have x to the a mod n. Okay, so think of this as f of a. Okay, so when we have a equal to 0, what's x to the 0 mod 21? It's 1. A equal to 1. What's 2 to the 1 mod 21? It's 2. Equal to 2. 4, 3, 8, 4, 16, 5. Okay, what's 2 to the 5? It's 32. 32 mod 21 is 11. 6, 1. Remember, that was the order of 2 mod 21. 7. Now we start repeating. 2, 8, 4, 9, 8, 10, 16, 11, yeah, 16 to the 32, we get back to 11, 12, we're back to 1, 13, 2, 14, 4. Okay, you see the pattern, right? We get this periodic function. Okay, what are we trying to find? We are trying to find the order. What's the order? Well, it's a period of this periodic function. So what should we do? Well, so here's a function that we can compute efficiently. What we should do is period finding. Right? So what do we do in period finding? We set up a superposition. We go into a sum over all a. And if we do this over a range of m, 1 over square root m, a equal to 0 to m minus 1. And then we are in this superposition over a of a, f of a. And then we measure this register. What happens when we measure this register? Let's say we get the value 4. So we measure this register and we get the value 4. Now what's our first register look like? Well, it's in a superposition over this, over everything where the second register is 4. So that. So now we get this periodic superposition. We have a superposition over 2, 8, 14. Right? It's periodic with period 4. And now when we do a Fourier transform again, it shows up the period. Right? Once we have the period, we find our non-trivial square root of 1 mod 21. And then once we find this non-trivial square root, which is 8, we look at 8 plus 1, take the GCD with 21, the greatest common divisor. We know how to do that quickly using Euclid's algorithm, which you learned in high school. Once you do that, you find a non-trivial square root of n. And that's your factoring algorithm. Okay, so what does the circuit finally look like for factoring? This is what it looks like. You start with 2 registers. The first one, you start with value 0, you perform a quantum Fourier transform mod m. This is the register which you contain the answer value when you apply. So now you put it through this circuit for computing f, which is f of a is x to the a mod n. You either measure the answer output to f, or remember, you can always discard it. That's the same as measuring it. Okay, so you discard it, and now what you're left with is this periodic superposition on these first wires. You put it through the quantum Fourier transform, you measure. Period finding subroutine gives you a way of reconstructing what the period is. Once you know the period, you take x to the period divided by 2. That's your non-trivial square root of 1 mod n. Okay. Now you take that non-trivial square root plus 1 GCD with n. That should give you a factor of n. But remember, it only works with probability half. So what you do, you take whatever this algorithm outputs and check that it divides n. If it does, you factorize n. If not, try again, because half the time it works. Okay, so that's it. You now understand the factoring algorithm.